Have you ever faced a critical production halt due to a dry tank because the pump won't turn on? Or perhaps a disastrous overflow caused by a pump that won't shut off? But what if you could prevent these instantly with a simple device? A float switch is a crucial component for material level sensing. It detects various media, including liquids, powders, and granular substances within vessels. It enables seamless, automatic control of the associated pump to maintain optimal fluid levels within the container. A float switch consists of several core components that work together for reliable level sensing. At its center is the hollow float, which freely floats atop the liquid. Inside this chamber resides the switch assembly, made up of a steel ball, lever, and micro switch, responsible for the electrical actuation. To balance and maintain correct positioning, the design also integrates an external counterweight attached along the cable, ensuring consistent float movement and signal precision. When the float switch is tilted downward, gravity pulls the internal steel ball, causing it to roll along its track toward the lower side. This movement engages the internal lever mechanism, thus actuating the micro switch. Conversely, when the float is tilted upward, gravity causes the steel ball to slide along its track toward the higher side. This repositioning of the ball releases the internal lever mechanism, deactuating the micro switch. The external counterweight acts as a critical anchor, defining the operational pivot point. Once the float reaches a set liquid threshold, this anchor induces a rapid, significant float tilt. This specific angular displacement is engineered to establish a precise switching point, vital for the seamless operation of automated fluid management systems. The intended use of a float switch determines the configuration of its internal contacts. These include normally open, normally closed, and the versatile single-pole double throw, each defining a different electrical response based on the float's position. In a normally open float switch, the contacts remain open when the float hangs downward due to gravity. When the liquid level rises and lifts the float to its preset switching point, the contacts close. Normally open float switches primarily serve two functions. First, they can trigger a high water level alarm when the liquid reaches the defined point, warning of potential overflow. Second, they are ideal for pump-down applications, where the pump activates to empty a tank once the fluid reaches a high critical level. In a pump-down application, when the tank reaches full level, the float switch closes the circuit, allowing electrical power to reach the pump and indicator light. This action begins emptying the tank and activating the high-level indicator. As the water level drops and reaches the preset deactivation point, the switch opens the contacts, cutting power and stopping the pump and indicator. Next is the normally closed float switch. In this configuration, the electrical contacts remain closed when the float is in the downward position under gravity. As the liquid level increases and lifts the float to the preset height, the contacts open, breaking the electrical connection. Normally closed float switches excel in two key roles. First, alerting to low liquid levels by triggering an alarm when the fluid drops below a set threshold. And second, managing pump-up applications to refill tanks nearing dryness, ensuring continuous operation. In this pump-up setup, a low water level causes the normally closed float switch to close, directing power to the pump and alarm light. It initiates tank filling and activates the high-level indicator. As the water level ascends to the preset activation point, the float switch opens, stopping the pump and deactivating the lamp. The last float switch configuration is the SPDT type, identified by its three wires, black, brown, and blue. In a low float position, the common black wire detaches from the brown conductor and connects to the blue wire. When the float rises to a high position, the black wire disconnects from the blue conductor and reconnects to the brown wire, facilitating versatile control switching. The SPDT float switch supports wiring for both normally open and normally closed configurations. This design allows it to be used in either pump-up applications for filling empty tanks and alerting low water levels, or pump-down applications for emptying full tanks and signaling high water conditions automatically. Consider this pump-up application using a three-phase motor pump. Start with the power circuit. First, the three supply phases enter a three-phase miniature circuit breaker. From the MCB's output, the phases connect to terminals 1, 3, and 5 of the contactor. The pump motor then receives three-phase power from terminals 2, 4, and 6. For the control circuit, a single-phase MCB is needed. The supply phase and neutral connect to the MCB's input terminals. From the MCB's outputs, the neutral wire connects to terminal A2 of the contactor, and the supply phase wire connects to the black wire of the float switch. Finally, the blue wire of the float switch connects to the A1 terminal of the contactor. The wiring focuses on the black and blue leads of the float switch, while the brown wire remains isolated. When the water level drops to the low threshold, the internal mechanism connects the black wire to the blue wire, allowing electricity to pass and trigger the contactor coil. It makes the pump to operate and fill the tank. When the float switch reaches the upper limit of a full tank, it disconnects the black wire from the blue wire, deactivating the contactor coil and causing the pump to stop immediately. For the pump-down application, the wiring is similar to the pump-up setup, with a key distinction in the utilized wires. The black and brown wires are active, while the blue wire is isolated. When the water level reaches its high point, the switch connects the black wire to the brown wire, energizing the contactor coil and starting the pump to empty the tank. As the water reduces to the low threshold, the float mechanism causes the black wire to disconnect from the brown wire, deactivating the contactor coil and thereby stopping the pump. At last, it's time to learn how to calibrate float switches. It would be better for you to become familiar with two terms. The first is the pumping range, which refers to the vertical distance between the float switch's activation point and the point at which it deactivates. The second term is the tether length, representing the physical length of the cable from the float switch to its fixed anchor point. Adjusting the float switch allows users to customize both the minimum and maximum water levels for optimal tank control. The lower limit is regulated by how much float cable remains inside the tank. More cable means a deeper allowable drop before the switch activates. The upper limit is defined through the counterweight's position. By shifting the counterweight up or down, the float's balance point changes. This adjustment method maintains constant cable length while offering flexible water level management in pumping applications. That's all for this video. If this breakdown of float switches clicked for you, let's make some noise. Slam that like button, blast it to your friends, stash it in your playlist, and hit subscribe to join the squad. It's your way of shouting, keep it coming. And trust me, it fires us up to drop more awesome content your way. Let's keep the good vibes going.